Yep. Can you please enable screen sharing? Thank
So
you.
should be okay.
All right. So thanks everyone for joining the session, ML paper reading session. So a big motivation behind understanding Clip and VQGAN is, if you look at few of the Discord channels, like the AI art community is just exploding, and like over a night you'll see a lot of posts, and I feel like a lot of exhibitions just can be curated from this artwork. So how are they using Clip? What is Clip, and how are they using another generator model combining with Clip to create such amazing artwork? So that's the focus of today's session. So if there are two key terms which I think I personally got away from Clip is, what is zero shot learning with natural language supervision, and another is, once again, contrastive learning. And I was not aware about this concept, so I looked into other papers and blogs to understand it better. So first we'll go through like very high level summary about the key aspect of Clip. So Clip is a zero shot classifier, and one could design their own classifier, and it removes the need of specific training. And as you might be aware that uh, in order to make your own custom trained model, you need a large data set, and there's another problem of labeling it. And also there's another issue of, if the test data set falls outside the uh, box, like data distribution, it fails to perform in real life scenario. So through this approach, it avoids uh, this kind of problem, and also it's agnostic, so it can be used for multiple different computer vision problems. uh, it has been inspired from a lot of research in the past, like from Conway self-supervised papers which were published like a couple of years ago, and they have developed this. And the way it has been arranged is, they have a list of classes. Let's say there are 10 class dog, cat, and that is fed into an encoder, and there is list images, and the image will match to the best class, like a photo of a dog if it's matching to a dog. So it's passed to an encoder, and it performs a similarity search to determine which text matches the image from the entire batch. So that's the core part. Uh, it also utilizes vision transformers. It's good that we covered that in the past session. So uh, to summarize, all that Clip requires is to pass the names of task, visual concept into the text encoder, and it will output a linear classifier of the visual representations. There are few limitations which we'll also cover during when we discuss the paper. What else are, yeah, the main selling point is zero shot image classification, and we'll go deeper into that. What is that concept, and contrasting contrastive learning, which is able to formulate the task of similar and dissimilar things of for an ML model. So it's when you have, let's say, a class image classification task, you have specific uh, labels for all of your data. Here, whereas we are doing like similar and dissimilar things, and let's go deeper into that, what it is. So for example, if you have an image of a cat, and you have a list of other images, and you want to find which images are similar and dissimilar, basically as human, we go and compare, okay, it's matching with this image which is another cat, and it's not matching with other images. Similarly, yeah, so contrasting learning is an approach of tasking finding similar and dissimilar things for a machine. So they have an encoder architecture to convert image into representation, and then similarity between two images, and generating training pairs. And to get a better idea about how contrasting learning works, we'll just briefly go through another paper called SimCLR and how they use contrastive learning. So yeah, as we saw, how it's a problem of similar and different uh, matching. So for example, how they do is in supervised approach. This is called a self-supervised learning approach. In supervised, you do annotation and you find similar and dissimilar. But if you want to do automatic, we follow, I think, this architecture where you first do augmentation on your data, which like transformation, offset, rotation. You pass it into an encoder, and this representation HI, HJ is used for downstream task. And again, they pass through this projection head to maximize similarity between images. So if I were to imagine this is, if you have a set of data and you're projecting into a high dimensional space, you want all the similar images to be clustered and maximize the similarity and other images to differentiate. So uh, that's if you want to visualize. So the way they are doing is like they have a batch size of 98,192, but just for uh, our understanding purposes, we can understand. Let's say there's a batch size of two images, and then they do data augmentation for each of these images into like more two images, and look and do crop, filter, color jitter. So there are total like four images, one for this, one for this. So after doing that augmentation, like there are, you pass into the encoder and generate this 2040 dimension vector, and you pass into the projection head and you maximize similarity. So there is only one pair which is the similarity, which is 1 and 2, and for rest of the pair they want to decrease and maximize the difference between those pairs. So using softmax, this is how we can do it. Mm, yeah, I think, yeah, basically once you train it, you can use this uh, representation for fine tuning task of classification detection, and it performed really well. So there are like two variants of this. One is like momentum contrastive, which is used in MoCo paper, but just to keep in mind. So we got an idea about what is contrasting learning, and I think this and zero shot are two main important concepts. So if anyone has any question, we could clarify it now. Else we can move on. Cool. So contrasting self-supervised learning is clear. Next is uh, we'll clarify what is transfer learning, what is one-shot learning, and what is zero-shot learning. And it, when I thought about zero shot, it's like you present to a new image to the train model, and it will be able to classify it. And that idea itself is so provoking. Like it's unbelievable. How could like a machine could just do zero shot? But then, yeah. So in in brief summary, one shot is you add one or few samples in the classification task. So let's say you have ImageNet model trained on 1,000 classes, and now for your custom domain problem, you have few more classes, or you just want like three classes of classifying furniture or buildings or something. You, you can add like one or couple of images and do one-shot learning. So it basically relies on knowledge transfer and other. Transfer learning is also, you can imagine if the train model is on buildings and you want similar like facade study, like you can transfer a lot of the features learned in that train model for your own domain. And there are various techniques, like you can remove the last softmax classification layer and replace it with your own. And during training, either you can uh, train all the weights, or you can freeze some of the weights of the network and train only few uh, layers at the back or in the front, depending on like what level features you want to train. So yeah, instead of training from scratch, you would do like transfer learning, because a lot of visual features from other train model could be adapted. So that is transfer. And fine tuning is like, yeah, I think the thing I mentioned was about fine tuning, that you get a train model. If the head doesn't match needs, swap the last layer and train it for your specific problem. So transfer, fine tuning, one shot. And basically there are five types of deep learning, which is covered in the blog: domain adaptation, domain confusion, multitask learning. We covered one shot learning, and then this is zero shot learning, which relies on no labeled data to learn a task. So how does this work, and how is it possible? So this blog covers goes more into detail. So imagine um, what we are in this example. They're using natural language learn embedding for zero shot. So if you are aware about models like word2vec, there are like vector representations like of your dictionary. Like let's say there are cat, dog, table, chair, and this is on natural language. And you have, let's say, another representation of your image data of dogs, chair. What we are trying to do is have a common space embedding, where while training, all the cat images like are being mapped into common space, all the dog images are mapped. So if there is a new image here which is not trained, it will look into that word embedding and find, okay, it's a chair, and give that classification, even if that image is not in the training example. I hope that's clear. So just to repeat that part, how to construct latent space and mapping from feature space to this space. Boolean, so the training common space I'm going to learn for, and words serve as label, and that word we have like already uh, models like word2vec, fasttext, Glowy, which we can use. And I think this image also gives a good idea that, say that this is a horse and this is a representation of the training data. If a new unknown test image falls into this representation, because this word2vec model, it will able to predict that, okay, it might be a cat. Yeah. So images are dog am I able. I Yeah. And then they go into few shot, and this is also a good finding I've that using like canon based memory of few shots, it's able to do uh, like a new training data, it's able to do few shot learning. But we won't go into this deep. So two main concepts: zero shot and contrastive. I hope that is super clear. Cool. Let's go deeper into the paper. So yeah, one important aspect of this paper is the generalizability part of the model. It's used for learn visual concepts, enabling zero shot learning of the model to downstream tasks. And it's able to do variety of tasks like OCR, action recognition, geolocalization, classification. It mm, it's task agnostic objectives. It's using I think this image would be better. So they have trained on, if I get like 12 billion image text pairs from the internet, and which is like a very large data set compared to other existing available data sets. And OpenAI uses the compute power pretty well. And as we saw in SimCLR, how they were using cause similarity between two images, like they're using this embedding of text, they pass it through the encoder and, and have this cosine similarity matrix. And if you want to check, I think this implementation gives a good idea that how image encoder, either using resonant or vision transformer, there's the line of code which does that. Text encoder, once you have this multimodal embedding, you you normalize it and then form pairwise cosine similarity, and these are the loss functions. So it's this is the core crux of the whole CLIP functionality. And then they're also sharing details of how to train 5 resonates and 3 vision transformers, and more specific data on how much time it took for them to train it. All right. Here, like they're sharing what are some past papers which were in this area and the limitations, and what are the important aspects. So I think this vertex paper is definitely, and convert. I think if in future, if we get time, it would be good to review this. So transformers based learning modeling, mask language modeling, and contrasting objectives to learn image representations from text. Mhm. From training raw text. Yeah, and I think because like there are also other multimodal techniques you can use, like text plus audio plus image, or text and audio. And using natural language supervision, it's the good part is like based on the corpus you have a finite data, and once you learn the embedding of all the words, it makes a lot of sense to direct the new image classification based on that those uh, vector representations. Training- Efficient method of learning from natural language supervision. Mm, yeah, and there are also uh, like n-gram is like, if n equal to 1 is like one shot, and comparing with n-gram learnings. And here is the graph which is showing like bag of word contrastive versus BOV prediction and transformer. It's much more efficient. Mm, 400 million, and we search for text pair in the yeah, I think one important thing which we like they discuss in the paper is like ImageNet had like just noun labels of all the classes, but they found out that having providing context text label improved the model accuracy like from around like 2-3%. So what does that mean is, instead of providing like a shape and compared to, like, they are using a photo of a shape or with some additional context, that is what they found was working well for the accuracy part. Only train a CNN and then to predict the caption of the image. Can learn better equivalent. Mm, yeah. Given a batch of any text image pairs, CLIP is trained to predict of which n by n possible image text pairings uh, across a batch actually occurred. Yeah. So out of all n by n, it will able to maximize the similarity of those one-to-one matching. In the same CLR blog, we saw n was equal to 2. Multimodal by jointly training an image encoder and a text encoder to maximize cosine similarity of text and image embeddings of n real pairs, while minimizing cosine similarity embeddings of n square minus n incorrect embeddings. So yeah, if you see the image, so all the non-white boxes n square minus n, they want to minimize. Yeah, cool. Um, they train it from scratch without initializing image encoder with ImageNet weights or text encoder. Yeah, temperature parameter which controls the logic in the software. So like some hyperparameter they mentioned. So about scaling the model, where they considered ResNet 50 with a transformer style multi-head QKV, and the second was vision transformer. One thing I recall that earlier works didn't had vision transformer. So while comparing uh, multimodal embedding space, and they considered and gave that. And this paragraph talks more into the training part. This goes into like advantages of zero shot transfer. Why is it important? And ado- task learning capabilities of machine, which we saw the paper in 2017, visual engrams for existing image classification. Mm. CLIP is pre-trained to predict if an image and a text snippet are paired together in a data set. So I think one thing which to keep in mind, clip itself like is not a generator model. So when I was talking earlier, clip plus VQGAN or clip plus DALI, it requires another network to generate images, and clip is like a guiding principle because it's on similarity of text and image. It's not like text to image. Instead of putting it and predict the most probable image text. Like I think this is the crux of like summary of what clip does. It's about pairing and most it gives out the most probable. So imagine if you have a text and a list of images, it will be able to uh, suggest which image is matching the most to the given text, and also other way around, where if you have list of text and one image, it will be able to say which which is the text which matches the most with the image. One important thing to note is like for zero shot evaluation, they cache the zero shot classifier once it has been computed by text encoder, and you use it for subsequent predictions. And then later they are comparing performance versus to visual engrams, and you can say it's outperforming. Yeah. Prompt engineering and ensembling. I think this is also very important. So I think I mentioned briefly that how like context was important. So when they were comparing with other data sets, one of the challenge was like multiple meanings of same word, and they didn't have like context in this one word. So in ImageNet, for example, construction cranes and cranes that fly, in depending on also the domain of the data set. So for example, for pet data set, boxer was referring to a breed of dog, whereas like for text encoder, which lacks context, it could be a type of athlete. So it was one common issue they faced. And they developed this prompt template, like a photo of a label that helped to specify the text and about the content of the image. And it improved like accuracy by 1.3%. And if we look for more data sets, also specifying a type of pet, like additional information after that context, it worked well, like for aircraft, food. And for OCR datasets, they found that putting a quotation mark around the text improved the performance. For satellite dataset, having like a satellite photo of a label, that prompt helped. Moreover, another, they have also experimented with other context prompts like a photo of a big label versus like and photo of small label helps to ensemble over the embedding space. These were two lines which I was not super clear to understand. So if anyone in the group has anything to explain, let me know. So it says we construct the ensemble over the embedding space instead of probability space. This allows to cache a single set of average text embeddings so that the compute cost of the ensemble is the same as using a single classifier when amortized over many predictions. I tried to look into like what are like some aspect. So if you are hearing latent space for the first time, it refers to the low dimension representation of the data. So you might have seen like many style GAN latent walks where they have this latent space and create animation in the walkthrough of that latent space. And you in those high dimension space can be also uh, projected into very low dimension using principal component analysis or Tisney. So let's say if this is 1,000 dimension latent space, when you project into 2 dimension for our visualization, you can see like a clusters of data. And when you walk through that, it creates that latent space animation. And I think the process of projecting this is called embedding, and this is called embedded space. Cool. Yeah, maybe I'll look into it. If I get more information about this, I'll share it later. Then again, like this goes into like performance of zero shot versus like all this available data sets, and it's just incredible that it was for zero shot it was better than many of this data set which had like fully supervised learning. So all this data set had classes of labels that okay, this is class A, B, C, and clip which has not seen that class in the training, and for that zero shot it was able to perform better. And it, like there were a few data set where it performed bad as well, but it's just incredible to see how a zero shot could also perform better than supervised. And it depends on like uh, how many labeled data sets were there for ones which were not performing well. One thing which they didn't figure out was so zero shot clip performance compares to few logic. Yeah. So for like one shot or few shots prediction, zero shot was performing better than those, which is very counterintuitive. Where if there is zero shot and if you see one shot, then obviously one shot would be better than two shots. Training would perform better. But their finding was zero shot matches the performance of four shot regression in the same space. So I think they are gonna look more into it in future. So combining the strength of, and one thing they wanna explore more is how to combine strength of zero shot transfer with flexibility of few shot learning for their future work. It's weak on several specialized, complex, and or abstract tasks. This is one of their finding. Uh, this is also a really good chart where they compared how many images they require to match the accuracy of this data set. So the median phi of the all list of data set shows that like if you provide five more images to clip, it will be able to perform the accuracy level of all the supervised trained data sets. So like this data sets like require the 2.2 images, and there are few which requires a lot. So it shows how like for most of the data set, it doesn't require many images. Collinear advancement. Hmm. What else is important? It's a data agnostic pre-training approach. Learns wider. We saw that earlier. And these are like they're comparing with other uh, state-of-the-art computer vision models. In this section, they check like robustness and clarify what is effective robustness and relative robustness. And yeah, deep learning models are exceedingly adept at finding correlations and patterns which hold across the training data set and thus improve in distribution performance, and largely drops for performance on other data sets. Whereas CLIP, which are like trained like supervised on large data set and capable of zero shot, is more robust. Mm, More robust to distribution shift than standard ImageNet. And these are like few questions which they don't have answers at that at even they don't have answers at this point. Mm, cool. Comparing with human performance, I think like the core concept of the paper we have covered. Yeah, few limitations, like as we saw, like for complex specialized task, it was not uh, performing well compared to other state of the art models. It generalizes poorly to data that is truly out of distribution for it. For OCR, they found that it was not performing well for handwritten MNIST digits, uh, which is embarrassingly simple for logistic regression. So it suggests that there is some brittle generalization of this model. And they they're sharing that for image captioning, which can generate novel outputs, there's some restriction on the zero shot classifier based on like the way they give uh, text prompts while training. So it could be for inference time over many languages. Yeah, combining CLIP with self-supervision and self-training is a promising direction for future, creating a new benchmark of task to evaluate zero shot transfer capabilities would help. So they are sharing that selection of evaluation data where could be a potential issue. The data uh, curation is like unfiltered, and they took train text image pairs from the internet. Um, and many complex and visual tasks can be difficult to specify through text. Yeah, the broader like takeaways is like one could create their own classes for categorization without a need of retraining. That's a big achievement from my perspective. Non-trivial zero shot generalization can do image retrieval, which we discussed. A lot of other tasks it can do. They even in this section they discuss the performance on for biasness uh, in the data set. So they check like Fairface and another data set to check whether it's biased or not. And as for our deployment, then it's very dependent on how we design the class. So they're mentioning that part. So and another like common application of this would be in surveillance, and this content discuss that part. Mm, It's using natural language as a training signal for learning about a domain other than language. Then they are like with reinforcement learning environment, it could be like demonstrate exciting emergent behaviors. That is, this would be a good paper to review in future. They talk about verbally supervised learning, like from internet search queries. It also uses search queries as part of a data set. This is another paper which goes deeper into that aspect. Learning vision models from scratch via natural language model does not densely connect the two domains with a joint attention model. Yeah, similar. Wide variety of tasks, zero shot transfer. Yeah, it's a 26-page paper, so I hope we covered all the important aspect. Cool. Any question? If you want to learn more about contrastive learning, this is a good review paper. It shows like different types of learning and contrastive loss formation. This is with image with audio, various data augmentation part, and this is using global context vector and yeah, future instances, context instance relationship, positive and negative. All right. So this was the first, and they have like open source the model, and if you wanna, there's also collab script, and it's very straightforward to use, where you could download the model, and as we saw, there are 5 ResNet and 3 vision transformer model, so you can use anyone. Uh, Processing of the image, and I'll just give you like how to implement. So I won't go line by line, but this is how uh, give text descriptions. They have a list of images, and then it will be able to match those. And as we saw in that paper, like can create like once you do that text or image into encoder, you find that embedding, you project it into a joint embedding space, and then you can find the similarity. And yeah, there's a cosine similarity matrix, which is a good visualization. And this is like zero shot classification. It shows like which class it matches the most. And you define the class, like they are importing all the classes from CFR 100. So it takes the image, goes through all the 100 classes, and outputs which class is most likely. So here it's, yeah. So this is CLIP. It has been a while I reviewed this taming transformer, but the whole one of the intent I had was we know like a good high level overview about both models and how it's working together. So I'll jump directly into, I think maybe I have VQGAN explanation. Yeah, these are like four core ideas. Learning, uh, yeah. So I think it's good that we first discuss. What so like it combines the effectiveness of inductive biasness of CNN and expressiveness of transformer. And transformer has it's computationally very heavy, like quadratic. So in the paper, instead of transformer over the whole image, they do transformer over a small patch of image. And what I mean by that is this part. So instead of like they have this sliding window where the transformer pays attention to those neighboring pixels instead of a bigger. So making transformation learns a rich context vocabulary of discrete code, and transformer learns to model their composition as high resolution images in both conditional and unconditional. So main ideas are learning an effective code book of image components. So what is code book? This vector here is code books. So basically it's vector quantized. So it's breaking out the image into discrete parts, finding which part is matching to the code book, and taking those number vectors and assigning it over here. That's the quantization process. So if this n minus 2, maybe it's representing 4 here, so it's matching that. So this whole pipeline is image uh, reconstruction. So encoder, decoder, and then there's also VQVA, and then in this VQGAN they added the discriminator part. And one thing to note is in GAN you have the whole image as discriminator, like a real or fake. Here we have like a small uh, space which is like real or fake for each segment, I would say. It's like a thing 16 by 16 and with 300 depth of feature space. So perceptually rich code book. So yeah, they added this loss. What else? Hmm, yeah, sorry. Transformer requires a sequence of tokens. And yeah, I think if you look at training process, they have one. Yeah, I think it will cover it in the paper. They have two-step training process. That's why. So learning a perceptually rich codebook, latent transformer, which works with a sequence of quantized tokens from the learned discrete codebook in an auto-regressive way. I should make this smaller. Oh my, and conditional synthesis. Yeah. So in the second stage of VQ, like the network tracking, they pass conditional text uh, token for training for the transformer. Special conditions for second we can is learn to obtain additional tokens that are simply purpose. So I'm not going to spend much time on this, but let's go through the key concepts. So CNN, we saw the limitations. It has spatial invariance, but it's very effective in learning. Local interactions matter more in low level. Transformer, no inductive bias, but it's very computationally more expensive. So they're combining both strength of CNN, CNN, and the transformer. Yeah. So phase one of training is they are learning the code book and the weights of encoder. And there's a loss definition. Phase two is conditional VQGAN for the transformer sequence token. Yeah, convert SI to by simply looking into corresponding embedding, and this is that part. And generate image patch by patch, because we saw transformer to reduce the compute load on transformer. So yeah, so if you see here, and the image patch is here, it looks at this 3. Then when it goes, the sliding window goes, it looks at more this 4 context. All right, so VQGAN, pretty good. It can be used as it learns long range interaction, which is I found quite important. So even if like the transformer sliding window, let's say you have a sentence that a tree on a hill with a house on this. So there are many long range dependencies in the sequence you have mentioned, and how that is translated into an image. That's why transformer with that attention uh, gives that advantage, because there were earlier model which are like image to text, but without that long range dependency, like it affected the quality of image. So I think latent transformer, perceptually rich codebook, and condition synthesis. These are the 3 like main uh, takeaways from this paper. In they have shared multiple codebook, and when they say 1024 or 16384, it's the size of the codebook, which is this. You can use this quantized model. And there are also collab notebooks shared on GitHub. So this goes into the reconstruction capabilities. So you load the VQGAN. You can also use DALI. Okay, why they have shared the DALI reconstruction? But okay, yeah. Basically, encoder, decoder with DALI. DALI is text to image, or sorry, image to text. And they are comparing how the detailed reconstruction of various this 2 VQGAN model and versus DALI. And this is the thing, like if I have shared a presentation I gave on Hitchhiker's Guide, but recently, as we saw that AI art channel exploding, people are combining VQGAN and CLIP to produce amazing prompt. And this is a script shared by Catherine Crossan on Twitter is the name. So where what they're doing is the main idea is, oops, what was they have this VQGAN model. This is the, okay. I just want to share one core concept, how they're calling. So using text prompt perceptor, which is our clip model, they're encoding it. And from that prompt, they're like using VQGAN to generate that image. That image is being encoded in this prompt by CLIP, and depending on the loss, so yeah, perceptor is encoding that image, and this is the training loss. So yeah, I and okay, Theodore has this collab screen. Theodore has worked on this part and contributed to few open source communities. So if you wanna jump in, like uh, I'm not super well versed in the each aspect of the code of this too. So if you wanna explain, that would be great.
Ah, you mean the notebook?
Yeah, like
Yeah, I think
walk us
what
through.
I'm not I'm not entirely an expert, but I think I can walk through. Like what happens essentially is you give a prompt, right? You give a text prompt, and you are using two things. One is the clip text encoder. So what Mayur was saying just now, like there were two parts in clip. There is one thing that encodes the text, and another that was a VIT, a vision transformer that encodes, the image. And we use the text encoder here, and that encoder is coupled with another model, which is in this case is the VQ-GAN. And you give it a text. You say, give me a beautiful day at the beach, and then you use some sort of pre-trained model, the VQ-GAN. The ones in the notebook, for example, are the ones provided by people. You can use them. It's from ImageNet, like general images, right? And so what happens is you create an embedding out of this text prompt with clip. It creates like, and then you try to, with, I believe there is a sort of optimization. It's called gradient ascent and not descent. You try to minimize, essentially the whole purpose of all this is to minimize the distance between the text encoding of the embedding of your text that you put and the image embedding, in a way, right? That's what happens. Like you minimize the similarity. You try to make the image that comes out of your generative model, your GAN or WikiGAN, to be as similar to the text input by Clip. And you can do that because Clip was trained contrastively. The text and the image, they are both at the same space. Imagine like that, because Clip did it end to end, like at the same time. I think it learned to embed both text and images in a similar conceptual space, embedding space. So you can do this sort of similarity minimization, and that's what the code does, the ascender. And it has some other tricks that you don't need to know to use it. You can literally use this, by the way, just by pressing play, 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 play. And at the end, if you scroll down, there is where you put your text, I think it's actually up here. So the prompts there, one cell below, sorry. uh, so those prompts, the first day of the waters, you can put whatever. That's River's prompt, like her favorite, but you can put whatever you want, and it will create an image for you. Right? It's really cool, and it does exactly this. It tries to minimize the other nice things that it does. You need to run preview. Okay, you run all. The other nice things that it does is some sort of augmentation, because like this doesn't really work if you create an image and try to optimize. The tricks are, you cut the image into squares. Why? Because that's how VQGAN is, right? Mayur was saying is discretized. And then you optimize each of the squares. And then there are some other tricks like, random noise, I don't know, like cropping and scaling and all. You just try to make it harder, I think, to the optimization to not fall into a local minima. Because like, I think if you just leave it without documentation, you will just find a very local, like, a way to that's very close to your text, but it's not really an image somehow. I don't know, like maybe some data information. So yeah, and so it's pretty cool. Just use it. Like I think you run it now. So more or less that's what happened. This method is called, I think this is the codebook sampling, right?
Mhm.
So it does this thing like where you have a sort of probability. So what you do is you cut the image into small like squares, and then you have kind of like a softmax, a probability to select which code book in dice goes to each of these cells. That's what happens in the generative, in the collab, let's say. So in a way, the model is trying to create an image that looks like a prompt. It also tries to choose the code book indices from the model that fit. And this code book indices, you can think of them as words. Only instead of words, they are like, visual representations. I don't know. There's some sort of like vector, but they're kind of words in the visual domain. Yeah. So, or let's say embedding of visual domain. So yeah, that's what happens there. There is another method also, the Z plus Q, but that's, yeah, there's just other like embedding spaces they do. Like it's not so important. But yeah, the cool thing is that you can run it yourself. Like just put any prompt you want there, something like really cool, and it will generate it for you. I don't know why it hasn't progressed. Maybe still downloading. Yeah. Yeah, because a lot of people download these models. You can actually, if you like one of these models, for example, you can, comment the rest, delete the rest, and it will finish faster.
Yeah,
Uh, yeah, something like that. So yeah, that's what's going on there. It's really nice method.
yeah, and I think one concept which I think is good to discuss and explore is the gradient ascent. So I think what you have this forward propagation in the network, which based on the image, it classify into different classes. What gradient ascent does is, if you want to maximize a particular class, how you should modify the image iteratively so that it maximize or it fires a particular channel or neuron maximally. So that's why when gradient ascent, if you say, from my understanding is, from the image text token of, let's say I want a ship in the mountain, the ship and mountain classes uh, f- for that gradient ascent will be maximizing to create that image, and there will be present. And this is like what machines understanding of these various class labels. And it's important, I think, to visualize this, because for example, when we are training, there was one example that, let's say we want training on a human face, and in your training data set there would be a lot of background noise, and we hope that during training the machine will learn that and ignore any background noise. So there was one incident that there was dumbbells training, and in each of the training data there was like dumbbell followed with um, um muscular hand. So when they did feature like visualization of that class, they found that the machine has learned that inherent biasness in the image. So it's, rather than assuming that okay, machine might have learned this kind of features, you can visualize those what the machine has learned in each class. Yeah, and I think there's also a good article on Distill which goes deeper into like at at different levels, neural channel layer, grasp probability. You can even play with the collab notebook. Okay. Now it's generating. Uh, yeah, I think that's it. I have for today. Uh, I'll be honest, like clip and taming transformer were a bit challenging paper for me to learn and understand. So if I didn't do anything, you can recheck if I was not able to explain any concept better.
Hey, thanks, Mayu. Thanks. No, it was great. It was great. I mean, it's a yeah, it's a big thing to try to explain. So it was great. I don't know if anyone has questions or we can discuss.
It was a lot.
Yeah. One thing you
Welcome.
can do is you can try the collab. It's actually free. Like if, with free, it should run. So even with just the Gmail, you can try it on the spot. Uh, but yeah, if there's anything you want to discuss or ask, please.
Yeah, and I think if you like experimenting with this kind of models, uh, I would if I would encourage to join like Discord of Ryan Murdoch's, and there's a long history about how this whole phenomena started. Of They started with like a slurp generator, and then deep days and other development which followed, how you can combine clip with other models and produce good artwork. So
Yeah, yeah. So yeah, this sort of examples you can create. Yeah, really beautiful things actually. Even with that code book is that notebook actually is quite good as well. It might not be as good as this one immediately with those settings, but you can create some nice images. Yeah.
yeah, and I know I, I I know Theo, you explained it quite well. I just want to make a simple diagram of like what's happening. So you have an input text, let's say a ship in ocean or something, and we have clip text encoder, clip image encoder, uh, VQGAN text encoder, and VQGAN image. So we saw that for initial creation, is it transferring the text embedding to both, and then this text embedding is is giving VQGAN to generate an image, and then that image is passed on clip to compute the cosine similarity and loss, and then that is directing mode generation.
Yeah.
I-
Yeah.
Is that
For there is also another like Clip wasn't the first. Like Clip actually relates also to the other things that we discussed. So we discussed about scaling, right? About how things work if you have a lot of data. So the clip idea is actually quite simple. I think like that image with a table with a it's I mean in the paper they have an image where they show like it's a matrix and then there's a text and then visual. It's very simple idea. It's like take a bunch of text and take an image and try to bring them together, in a way, or like try to learn a common embedding. By embedding they mean vectors, right? A common representation. So this thing here. So this idea, the contrastive was much many years before. And this is a very simple contrastive as well. There have been a few papers after Clip that try to improve on that. For example, they say, we do Moko the or like two or a lot of different stuff. Like we do this smart thing when we do the annotations. I don't know, but Clip didn't do any of that. It just did a very simple. Here's 400 million images, right? That's how many it was trained of text and thing and image and learn, and it learned like incredibly well. So it's an example of what we are discussing the other day about scaling and simplicity and all this stuff, right? The first Clip like type paper, I think it was 1 year before Clip. It's a medical paper actually. It's from a
Mhm.
quite famous Berkeley professor, and I think it should definitely be there. Yeah. I
Yeah,
think it's Convert. I guess is it Convert?
Yeah,
No,
yeah, yeah.
it's not. No, I think it's. Let me find the name. It's a bigger blah blah blah.
Medical visual.
Yeah, I will find it. I have it here. 2000 contrastive learning of medical visual representation from paired images and text. This one, yeah. Ah, yeah, Convert. Yeah, you're right. So this is literally Clip, right? So they took. This is an interesting also application, practical, to see like what you can do with this idea because Clip sort of opened the Pandora's box, right? So everyone is doing now multimodal models because of this, right? So what they did here is they tried to solve a very practical issue, right? We have some chest X-rays, and we have a lot of language data that are not very pretty. They are not structured. We cannot run like regression or whatever, like on them, Excel sheets. It's just text. What can we do? So they did this exactly thing. They took all this text and they tried to learn a common embedding, and then they use that model downstream to do something, classification, for example. Can you tell me from this chest X-ray what's going on? Something like that. So it's a very nice application. And Clip literally, like OpenAI took this, the same thing. It's the same thing, and they scaled it. They just said, okay, let's do it everywhere. Of course, and they did a lot of tricks. They do have a lot of tricks to make it work at that scale. But still, I think the idea is valuable. Like you can think of a lot. I since I started with Clip and all these ideas, I'm thinking a lot about I'm always thinking about data connected now because of it. So you can think of a lot of ways you can combine language, especially with something in architecture and engineering. A lot. It's super easy, right? One is like, what I was doing with the layouts, like, just say, how many rooms are there and stuff. But you can do even more specific stuff, right? You have performance data, you have Beam, Revit models, I don't know, whatever you want. So I think it's a very interesting approach. And yeah, simple. Unfortunately, there is no code, but there is a community code that is out there. Let me give you the code. That is, it's just becoming good. Where is it? Kid.
Is it Eluther AI?
Yeah, it's Kate's code. Yeah, it's this one. Okay, train clip. This is the one. So if you ever want to train something, it's this one, right? And it only needs data which is like images and text. That's it, paired. So it's not very difficult. This sort of things you can try to experiment with because they are simple ideas. So if you see like how to train it is that there's nothing like a few lines or something. You just need to give it some data. But yeah, if you want to train, but it's a very powerful technique. Let's say, yeah, that's what I'm.
And you did a training with Dali, right?
DALI is different. Yeah, DALI is
Yeah.
also. I mean, if people want to use it, yeah, this is the implementation is really good. If people want to do DALI, this is like the code. You can literally do it. Like if you have the data, you can do it. It's super simple. Simple. I mean, the hardest part is the data in a way, because most people that do this clip and DALI stuff, right? They like general image generation. Like they like to make anything, right? They like to make like an ice cream on top of a hat, in front of a. It doesn't matter, right? But for me, I focus on domain specific, so on the narrow stuff. So DALI, yeah, you can do narrow. For example, the first image you see is the cubs, right? It makes birds, images of birds. So yeah, both of these are interesting. So yeah, it's a yeah. When I did the presentation, I think we did together, right, the same day in Digital Futures. I called Clip the most important model that exists, like open sourced in a way. Uh, until the next one, of course. But yeah, I think it is. It was mostly by mistake. But yeah, you should definitely at least. I really recommend you all try the collab notebook. because you don't need to do anything. It will give you an intuition of what's going on. Like literally at the last cell, you just type the sentence you think. Also, that it took me a lot of time. Now, this is the sentence I had, right? It took me a lot of time, and actually, this is part of why this clip generated art is really good now. There is what they call prompt engineering, right? So it takes a lot of time to understand what to tell to the model, how to describe what you want, right? But that's also nice. It's nice because a lot of prompt engineering is domain specific. Like if you want something, I don't know, design related, you need to know the words to use, right? And Clip knows all the words, right? It knows all the stuff you want to ask it. That's the cool thing. So yeah, I would definitely recommend like just play around like this, exactly this. You just put whatever something architecture. You press enter, it will make an image for you. It's really cool. Yeah. So I think that was
Yeah, and I think once you start experimenting, it provides a lot of interesting results which you never expect.
I have a question regarding those parameters like I and loss and losses. Like with more iterations, is it getting more and more closer to the prompt, or is it something to do with the resolution of the image?
yeah. Is the it closes the gap, the loss, let's say. So, like as we said, what this does is imagine like it tries to maximize the similarity between what you wrote and the image that comes out, right? So you can increase the iterations. In that cell, it says iterations 500, I think, right? You can put
Yeah.
like 2000 if you want, and the more the better, in a way, like usually, right?
Yeah.
If you do 2000, let me see, the way decay is okay. Yeah, I would do like this way decay, you can put 0.05, and the other one, the TV weight, you put zero point 0.1,
Okay.
and then you can put like 2000. And I would change the display frequency not to be every 50 because then it would flood your this means like how often to show you an image, like you can put
Okay.
200, and then it will create. Yeah, these are the options there, the parameters. And you can also select which model. Like now we are using, you see the 1024. This means, as Mayur was saying, it has 1,000 code book. You can change that name literally. If you go all the way to the top, you can see the names of the models, right? You can change it to the 16384 or something in the collab notebook. It has the names on the top, right?
Yeah.
And then it will use the better ImageNet, and you can get much nicer images. So the larger code book, obviously, but and you can create really beautiful stuff, and it gives very nice intuition of what's going on. Because sometimes when it fails, also you will understand what's going on in a way. Like, why is it showing me this instead of something else? For example, now let me show you how far the prompting has reached. Uh, Now is like it's actually a meme the way they prompt it now, but I mean it works. So something like that. I don't know. Instead
Yeah.
of words, instead of describing like a human, you don't need to because Clip is not a human, right? You can put something like this. So this is what people put. They put at the beginning the thing they want, and then they put V-Ray, CGI, all this stuff. Why? Because the quality of the image you generate is much higher. Why? Because Clip has seen almost every image out there. And it just so happens that the V-Ray and CGI images are very clean. They are
Yeah.
rendered. So when you put that, immediately the image you will generate is like clean and high quality, if you like that style, right? And then literally you can check, you can keep doing that, and you will understand how much Clip knows. It's like incredible. Like it knows, it understands everything, you throw at it. Yeah, almost everything.
Interesting.
Yeah. So
And also I have realized that many times if you monitor the loss, like after a point, if there's no major difference in the losses of your previous iterations, it's it's not gonna change much. So it depends on the prompt and your thing. But sometimes after 2000 iterations or 500 iteration, it's not, the content
Yeah, it
is
might not change a lot.
refining at a minor level. Yeah.
Yeah. If you wanted to like change slowly, you have to reduce the step size and stuff. Yeah. Like this is the, for example, if you play around a few hours, you will realize that the 1024 model, the ImageNet, it starts like a checkerboard. Actually, most of them. Why does it start like a checkerboard? Because in the beginning we actually try to split the image into squares, remember? So that's why, so this way you can sort of understand. This here is the first, like without optimization, this is how ImageNet embeddings look like. Imagine these are visual latent space, like I don't know, of the whole ImageNet, which is like a million images. It's always like this. So how many different prompts you put, the first image will look like this, right? And then it becomes this checkerboard slowly. Why? Because this augmentation that they're doing are exactly this. They split the image into small checkers, right? And they try to create in each checker, in each of these, they try to evolve it to maximize the similarity of the whole image. And that's why after a few iterations, it becomes like I think if you scroll down, it's very visible where it becomes very checkered. So that, yeah, here, right? And then it starts to slowly become an image, right? And it's really wonderful to see it, how it becomes an image, right? Because it will become an image. So the brutalist architecture, of course, it has seen it, right? So for example, now, can you try copy pasting this V-Ray, CGI, all this stuff next to your brutalist architecture? You see where it's at, right? It's already at a very good point. Like it has a perspective view of the building, right? You can actually tell it, right? You can tell clip top-down view or perspective view. Like this, it's incredible. Can you try and put like, this V-Ray, CGI, some of them next to it? I'm just curious. Yeah. The art station, I don't know. It's some sort of meme, but it's okay. I think it's a site where people. So yeah, I think like it looks like it's funny or something, right? But it really helps with intuition. Like I think it's the best way, might be the best way to get into deep learning right now. Clip
Yeah.
making art, because you actually are seeing the internals of the model. You know what's going on, yeah. Plus, you have a lot to offer, like all this stuff, like this prompting, right? I don't think the user who found it, he or she is like AI engineer, not at all. So, like, yes, Catherine, like Rivers, she created this code book, and it's necessary for us to create nice images, but 50% of the work is also putting all these prompt ideas, the nice, finding ways to prompt it, all this stuff. And this is open for everyone. Yeah, it's open for everyone. So yeah, it's nice. Yeah, so I recommend you to try. It's really fun.
Yeah, and a lot of time people also share the prompts they are using. So like depending on your intent, you can see like what is working well or not.
Yeah,
And
yeah.
now I think
This
people are more
one,
experimenting with the animations.
yeah, they're doing animation. Also, this one, if you her latest stuff is not actually clip and a model, she's trying to train something very different, like some sort of one-shot generation, like with clip. I don't know. That's why it looks a bit. It looks okay, but it's not like clip. Yeah, this deep image prior thing. I wonder. Yeah, what about the collab? Did he create the image? Would be nice to see.
Yeah.
Is it this one? Yeah, it's this one. So checkerboard again, right? Because it's always like that, and it's still running. Okay. So yeah, I mean, yeah, just play around. Yeah, experiment. I think it's super nice.
And it's also, I think, a fun way to get introduced to AI for creative purposes. Like
Yeah,
I have
definitely.
seen like script where people are writing song lyrics to generate a visualization for that uh, songs, and it's also pretty good.
It's
And
already
if
been
you are
used in
into
training.
this, also I think Daniel Russell is a
Yeah,
good
yeah, he's
person to
good.
follow.
He's good. Yeah, I mean also at Vernon, I guess. Rin also. Yeah, all these people. There's a big community. Yeah, of people now, and I do think some from architecture are also doing, uh, experimenting a bit. I don't think we are completely aware of all this in architecture. I think if people were, I do think they would be using it a lot because most people in architecture are much more artistic than I am, and I shouldn't be the one like using it so much, I guess. So I hope that if they realize that it's just a matter of pressing play and just play around, uh, you can create some really cool stuff.
Yeah, and maybe like experimenting with this type of words also helps one to discover like what is working well for the desired graphic. So it's a lot of experimentations overnight. You will get better and better, and if you know deeper understanding, then you can play well with the prompts too. Oh,
Ah, sure, I will share it. Yeah, I can put it on general maybe. It's no problem. Collab. Ah, wait. I think we have notebooks. Yeah, yeah, of course. I will paste it in the notebooks.
Yeah, I can see really high resolution images after adding those
Yeah,
prompts.
you see what happened, right? It's
Yeah.
completely like it's a render essentially. Why? Because Clip probably saw, I don't know, a few 100,000 renders or like something like that, right? So now it's like the quality is really high, but we didn't know that when we started. When we started, we were just prompting with words like, okay, let's see what it can make. Then people, okay, can you do perspective? Okay. Then people started doing, 3D render, and then they started all this stuff, V-Ray, CGI. And then you create interesting things. Yeah.
and like I believe in the training data set of image text pairing, there would there might be images of like a perspective of something or a rendered image of something, and that's why Clip has learned that correlations that okay, render is like very high detailed images and perspective is this angle.
Yeah. It knows everything. It's pretty crazy. It's crazy. Yeah.
Yeah, I was so surprised when I typed Zahadid's prompt and it literally created an image of Zahadid, and like,
Yeah.
whoa, how come the model knows even
And
that domain?
it's interesting also how people react to it because a lot of people obviously maybe haven't seen it, so are not aware that there is a thing like this, right? But I remember when it came out, right? There was this image where they put an apple. So Mayer was showing this zero shot classification, like classifying images without even like Clip was never trained to classify anything, right? And we ask it to classify something random and it doesn't. So people showed, oh, but if you put an apple, right? And what did they do? I think they put some text on it, like they put like they put an apple on a text. And what is that image? It's a famous image, right? Like a failure. And it did like an Apple MacBook or something, right? Instead of finding the correct, right? It put an Apple MacBook. But then, and I don't know if I can find that image. And everyone was like, "Oh, look, yeah, iPod, yeah, of course." Everyone was like, "Oh, look, it's actually not so intelligent, right? It's very stupid. Why does it say iPod there?" First of all, it's not. It's actually a very nice semantic correlation, right? It's actually Apple there, right? So it does make sense to say, iPod. The second is that someone made another test, and I forget what they did, that sort of completely disqualifies this. Like, yeah, they changed the classes. So this is amazing. Yeah. So what they did is they took the same image and they put another class that literally said an apple with iPod written on it, and Clip chose that as the class, right? So it was a matter of, like, you didn't have the correct classes to find the class. It was just a matter that it found, from the ones I had, the iPod was the closest one, right? But then when they the same image they said an apple with iPod written on it, then Clip chose that, and it's really incredible. It's really, because and it's a nice interaction, because I see this a lot with like AI lately, and there is a lot of like disbelief and stuff, like, and criticism, which is okay. We should be critical, but there is also like a bit in a wrong way, in the sense like, yeah, this is not, look at this one thing, it disqualifies everything. So I think we should be a bit more critical, and like try to understand why it happens and all this stuff, right? And this was a nice example, yeah, because I saw, even typically you see on LinkedIn, right, or sites like that, where people want to shout something like, "Oh, look at this, it fails." But if you try to understand, it's much more valuable, I think, than why it fails. Yeah. So
Yeah,
yeah,
I think like for initial exploration phase, like one might not encounter this, but if you are deploying it for some use case in your domain, like having knowledge of how to design those classes, what will work, what are some like outlier or error cases, it like theory background would be important.
yeah, yeah. And it's
Like,
important you can build models similar, not to create images, but to guide or classify. You can build, like, for example, right? You could, if you have like a lot of messy architectural data, and you don't know how to train a classifier to classify your designs based on typology, I don't know, or your spaces based on, you know, um, program, all this kind of stuff. You can simply do something like this, right? I don't have a lot of clean data, but I happen to have a lot of metadata, right? So here it is. Here's my image, and here's all the metadata, and stuff like that. Try to learn, and then it won't learn to generate, beautiful images, but it can learn to classify. So this approach has a lot of potential, I think. Yeah.
yeah, I see a lot of maybe interesting applications developed out of scraping data from like architectural websites like ArchDaily or Domus. If they have like text description for each of their images.
Yeah. So yeah, this is, I think, it's a very nice introduction to AI. I would definitely do it. Yeah.
Right.
Okay, I will stop the recording.